So here are the solutions to the resonance homework. I'll get through them quickly. I probably won't do every single calculation. I'll set it up and then I'll talk through some of the explanations because I'm going to guess those are the ones you were at least sure of. Okay, so the first problem, we want to know if the cat will get 5 joules of energy for each push. And the key here is timing is right. This is an idea of resonance. You have to push with a frequency that matches the frequency of the swing. And the frequency of the swing is determined by its period, and we want to recognize here that this is a pendulum. Okay, so there is an equation for a pendulum for its period. Learned that last week. That's 2 pi radical L over G. All right, so if you plug in the length of the swing, you put in G, and you solve for period, you'll get a number. I don't remember it off the top of my head, but what you should understand is that the frequencies which you're looking for is 1 over that period. And 1 over the period should give you a frequency of around 0.41 hertz. I don't remember off the top of my head. But the point is, the frequency at which the cat swing oscillates back and forth does not match the frequency at which it's being pushed. So if they don't match, you can't get a resonance, which means you're not going to get this amount of energy, the 5 joules per swing. Sometimes you're going to add to it, sometimes you're going to subtract because the timing is off. Okay, that's the idea of resonance, where you have a fairly straightforward calculation involved. So keep in mind, you should be aware of those period equations for a mass spring system or pendulum when they arise. They're in your reference tables, so they're easily found. Okay, now let's say that TEP realizes a mistake, and rather than push with the frequency of 0.30 hertz, he decides to push with the frequency of 0.15 hertz. How many oscillations will have occurred before it gained 45 joules of energy? Well, 45 joules of energy is 9 times 5 joules. Okay, so essentially he needs to give 9 pushes at the right timing. But that doesn't necessarily answer the question. We want to know how many oscillations, not how many pushes. And so that's where the 1/2 comes into play here. The idea is if he pushes with 1/2 the natural frequency, then he's basically pushing every 2 swings. Okay, so reason that out in your head. So if he's pushing for every 2 swings and he needs 9 pushes in all, that means there's going to be basically 9 pushes, okay, at 2 swings or 2 oscillations per push. That's based on the half the frequency. Multiply those two together and you get 18 swings or oscillations. Just put OSC, okay, because the pushes cancel out. All right, now we can go into some physics that we've learned a while ago. It's a good review. What will be the change in height if you get 45 joules of energy, right? In other words, if the bottom of the swing is here and we're pushing and pushing, we know that it's going to go up higher and higher at some angle and some height. Well, the height part should be pretty straightforward. What we want you to recognize, since you're told energy and we have a change in height, this is basically our energy is going into gravitational potential. So we can say whatever energy we have gained, which is gravitational potential, is equivalent to mgh. Okay, so h is what we're looking for here. So we put in 45 joules, put in the mass of the cat, 4.5 times 9.8. Solve for h, and I believe you get 1.02 meters. I know the answer key says 1.05. That was a typo on my part. Okay, now the angle part is basically what this diagram here, as ugly as this is, and you got to do a little bit of work on this. It's a good problem. It's been a while since we've done that, so let me switch to this screen here. So this is the idea again. We have a pendulum of length L, and we know it swings up to some height. So let me draw the pendulum again right there. Okay, and again, this is the angle that we're looking for. And what do we know besides the length? Here is the length of the pendulum again. It hasn't changed and swinging up. This is the height that we've gone to. Well, we want to use trig, and we need a triangle, and there's no obvious triangle here. So the triangle we want to create, this is a wedge, we really can't use that as our triangle, is something like this. If this distance from here to here is h, then from here to here, okay, is L minus h. okay, such that this whole distance is L, so we get that. And this might remember this from ballistic pendulum problem. So I've got just another side here. I'm not going to worry about the value of this. And here is my theta, once again, opposite interior. Okay, so now I've got this triangle that I'm outlining, and I can say the cosine of that angle equals L minus H over L. All right, so basically my answer for theta is the inverse cosine of the length of the pendulum minus the height that we figured out in the previous part divided by the length. And you should get an angle of around 70-something degrees. All right, next question. In reality, it's not likely that the cat will have that much energy. And what are two reasons for that? Okay, the one obvious answer, and I'm going to imagine many of you put, let me see if I can scroll this down. Okay, is you're going to put something like friction energy loss, and that's true. The technical term, and it came up briefly in the tutorial, is damping. Okay, there's external forces, sorry, that should be damping, in the system coming from a variety of places, the hinges, air resistance to a lesser extent, that inhibits the growth of energy from each push. Okay, so that's the obvious one. The less obvious one, but just as important, is that it's very difficult to push at that frequency. Difficult to push consistently at the natural frequency. Okay, so if we know the swing goes back and forth 0.41 times a second, it's very difficult to push with that exact same amount. So each push, if you're off a little bit, you're not going to quite get the full 5 joules per push. Okay, next one, related to earthquake destruction. And it asks outline what resonance is. And this is important for the AP, your ability to take something, define it, and break it down. So first and foremost, what we want you to remember is resonance is an amplification effect. It's a constructive interference. So you need to make some statement of that sort. That's the one that kids most often leave out. Okay, so it's an amplification of wave. Why does it occur? Now that's what the other two bullets are for. It occurs when the driving frequency, okay, or some reference to, something akin to that, you don't have to use those exact words, matches, and that word matches, or is close to, again, something to that effect, the natural frequency of the system. So that term, really important, need to show up and realize that resonance is due to matching of two frequencies, a driving frequency and a natural frequency, and the result is an amplification, okay, which is a constructive interference. You don't have to use the word constructive interference there. I think you'd be all right. Okay, now let's continue on with some application of this. So we talk about here destruction of buildings. Why might this occur? You might have thought prior to this, well, any shaking is going to be bad for buildings. Well, generally that's true, but it's the resonance of particular frequencies that causes an amplification that causes the buildings to sway much more than normal, which can cause a damage. So basically what they're asking you to do is look at this data and say, is there support for resonance occurring? So resonance means you need to compare two frequencies. Well, we have the oscillation itself, and then we have the building, and then we have the earthquake waves. These are the driving frequencies here. This is the natural frequency. So if the period of the oscillation is 2 seconds, then the frequency, the natural frequency, I'll call it Fn, is simply the reciprocal of that, or 0.5 hertz. So you should show work for that. And then we want to find the driving frequency. Well, the driving frequency, well, what do they give us? They give us speed and wavelength. So hopefully the wave equation pops in your head, and we can say frequency is velocity divided by wavelength, which would be velocity is 6,000. The wavelength is 12,000 units, and that's 0.5 hertz. So you show that there is a match in frequencies, and then you explain that since the driving frequency matches the natural frequency, you're going to get resonance, which is an amplification, which will cause more damage than normal. All right, the last one is a little bit of a subtle thing, but I think it's kind of a cool application. Something I would have liked to have shown you in class, but I couldn't. And it's how radio receivers, or even televisions for that matter, pick up a particular signal when there are many out there? How does it choose one over the other? Well, it's ultimately about a resonance. So again, if you read carefully, I've set the dial at 91.5, which is a frequency, megahertz. So in a Rochester area, let's say there's 20 different signals powerful enough to reach my home. Why, when I set the dial to this one, do I pick up the 91.5? How does the radio circuitry know to pick up that one? Well, if you read the first part, it's basically is that 91.5 megahertz signal that's coming from the BER broadcast place in Fairport, New York, will, well, let me put it this way, the antenna of the radio picks up all those signals. But this one is the only one that will cause a resonance in the actual circuitry. So the circuitry is designed to act like an electronic spring, okay, of a particular frequency when you have the dial at that setting. So when we have the dial at this setting, then the circuitry will resonate at this, or has a natural frequency of this frequency. So an incoming frequency of 91.5 megahertz will cause a resonance, and that will amplify over all other signals, and that's the dominant oscillation within a circuit. In other words, we picked up that frequency only and we ignored all the others. All right, so I know I said a mouthful there and I've only written a little bit here. But what I want you to understand in this problem is that the resonance in this case does not amplify the sound. The sound comes from the speakers. It's not in the radio waves themselves. Radio waves is a form of light, not a form of sound. You can't hear radio. So what the idea is we want the incoming signal to cause an electronic resonance. Therefore, that resonance stands out over all other tiny signals, if you will. And therefore, that's what's going to get played. Okay, if you have any questions, you know to email me.